Okay, time for section 1.3. Now, this is when things are going to get a little, because I'm trying to still help with the postulates and theorems and definitions without actually showing you all the postulates and theorems and definitions. I'm hoping you pick up on how to make them short. But there were some that were pretty important that I wanted to make sure that you picked up on correctly. And I didn't want you to waste a whole bunch of time. So whenever I talk about postulates, I'm going to try to make sure that I put it in purple, which is what that color is in case you can't tell. And whenever I talk about definitions, I'm going to try to make sure it's in this color because it's the closest I could get to yellow that you could actually be able to see. All that being said, when I give you a shorter way of saying something, you should probably use that shorter way of saying something. You should have already watched the video where you saw me do all the highlighting for this section, but I didn't tell you anything about how to write anything, and that's because I don't want you to have to write anything down after those videos until you've watched this video, because that may sure up some things in your mind, and you might not have to write a whole bunch of stuff down. I don't want you to write a whole bunch of stuff that you're never going to need. It's just going to be hard for you to weed through. So there's no point in that. I want you to wait until the end of this video and then see the things that you need to write down. Understand that for postulates, theorems, and corollaries, you should always write those down. Not all the long stuff that they have in the book, but a shortcut for every single one needs to be in there. If I highlight it, you need to have a shortcut for it in there. Definitions, you get to kind of pick and choose which ones go in. So if you already know what it is, there's no need for you to worry about it. But if I make a point of writing it on the board, then chances are you don't really know it the way I need you to know it. So while you may get it now, it might be good for you to write it down. So you might want to make like another little mental note that, oh, this one's really important. Let me make sure I write it down and the way she specifically said it instead of just the way I think it means. Okay, so there's that little conversation. Now, usually I'm going to try to work in black because it shows up really well up here, and then you can tell what's kind of important and what's kind of not, but that won't always work because you understand that I don't really like black all that much to write with. Wear it a lot, but don't write with it a whole bunch because I'm a very colorful and expressive person. You know that about me. So you'll understand if I abandon the black for some other color for just ordinary notes. Once again, if it's important enough for me to write up on the board, it's important enough for you to write down in your notes, not to mention the definitions and postulates part. Okay, moving on. We can handle this. I promise it will not be this laborious later on. Later on, it'll just all kind of flow. Just give it a little time. So, starting with postulate number 6. They give this really long definition. What it means is that 2 points have to have a distance between them. It doesn't matter if there's a segment in between them or not. Usually there is because it's defined that way. But regardless, there has to be some distance between them. And we can find that distance according to P7 by using something called the ruler postulate. This is what they call it. That's kind of what you need to call it. It keeps you from having to write this really long thing down. Because while this is shorter than what they say, you know, you can subtract the numbers to find the distance. While that's shorter than the long definition they gave, it is not as short as the ruler postulate. But we need to know what the ruler postulate is. So make sure you write both of those down so we can get the idea of, oh, from now on, we're going to call this the ruler postulate. It's like the title of this postulate. So what all that means is when this is the problem, they talk about line segment AB, and you know they're talking about line segment AB because they have the little line up here. It has no arrows on it, so it must be a line segment. They're talking about line segment AB, and that's right here. And it has to have a distance, and that distance they call AB. There's no line on top. Whenever there's no line on top, that's when we're talking about distance instead of talking about the actual line segment. In geometry, they make a point of letting you know if they're talking about numbers or if they're talking about things. So when they're talking about numbers, that's when they're talking about AB with no line. If they're talking about numbers with angles, there's a little M in front of it to say the measure of that angle is. That means that they're talking about numbers, and you actually have to give numbers for your answer. But when they're talking about segments or angles or lines, they actually mean the physical thing itself, not the distance there. So it's a distinction geometry makes. So right here, the distance between A and B is going to be 2. So AB equals 2. And incidentally, BC equals 4, because that's the distance between them. Now, they do a definition, and your book does this twice so far that I've seen, and it'll probably do it again later on. So they do a definition called between. They keep throwing up the exact same definition, but they throw it up with different things. Like they talk about between with points, and they'll turn around and talk about between with lines, and then I bet they turn around and talk about between with angles, and then I bet they turn around and talk about between with planes, etc., etc., etc. So this particular between is defined as if B is between A and C, then the distance between the distance of AB plus the distance of BC is equal to AC. So up here, since B is between A and C, that means this distance plus that distance has to equal our total distance. That's all it means. I don't use the definition of between. I think it's weird. Sorry. I call it segment addition because that's actually what you're doing. You're adding two segments together. Now you're not adding the segments, you're adding the distances of those segments. But it's a shortcut, and that's what I do. I'm all about shortcuts. So in this case, the distance of AC has to equal AB plus BC. And by the definition of between, that's true. And we can substitute AB for 2, because that's what it was, and BC for 4, because that's what it was, and get that AC must equal 6. Now, I know you knew that. I know that's not news to you. I know you could have found that regardless of having a B there or not, because you just could have counted in between A and C. I get that. But actually laying it out like this has a purpose later on. So I needed you to get a little bit of the algebra in so I could make some connections a little bit later. Okay, on to the next little bit. We're going to use this definition of between for our next little part. Going to take it a little bit further and say if y is between x and z, then we know that xy plus yz, those are capitals, I promise. I'll fix them. They look like capitals. Now they do. xy plus yz is equal to xz. That's the definition of between. That's segment addition. If I were to draw this picture out, I have an x, I have a y, and I have a z. I'm going to tell you that x equals -5 and that z equals 15. And then I'm going to tell you xy equals 3a and yz equals 2a. I want you to find what point y is. So let's first figure some things out. If this is -5 and that's 15, tell me what xz must be. I say tell me like you can actually, but pretend that I can't. So tell me what xz must be. From -5 to 15, if I were to subtract those two, 15 minus -5 means that xz has to equal 20. Because minus negative turns into plus positive. So we get that as 20. Now that we know that that is 20, and we know that this part over here is 3a and this part over here is 2a, we know that 3a, because xy plus yz has to equal xz. By substitution, I could say that xy plus yz has to equal 20. Then we know xy is 3a. Oh, that is not a 3, darn. And we know that yz is 2a. So 3a plus 2a has to equal 20. 3a plus 2a is really 5a. Which means a must be 4. Well, that's great. If a is 4, then that means that since xy equals 3a, that xy must really be 3 times 4. So xy really equals 12. And -5 plus 12 is really 7. So y must be 7. Talk about showing every step there is. There's a reason I did that. When we get to doing these problems later on, they're going to want you to write down why you know all these things are true. So you're not just writing the actual answer algebraically. You have to write down all the reasons for why they're true. So some of those reasons are going to be simple. For example, this one is postulate 6, which means it's our distance. Definition of distance. This one was simply addition, simplifying by addition. This one was the definition of between, or our segment addition. This one was just plugging that in. We said that that was equal to that, So this must equal that. Transitive property. A equals B and B equals C, then A must equal C. Transitive property. This one is replacing values that we were given in our problem. That's just substitution. This one is addition, combining like terms. This one was division. From algebra, but it was there, their division property. Up here, we stated what was given. So we just say that it was given. Here, we substituted for that substitution. Here, I multiplied or simplified. Here, I plugged in our information using the whole definition of distance again. So y must be 7. I simplified. Now, this is a really long proof to prove what we found is that y was 7. So over here, I can come and put 7. Now, I felt great that we found the answer and all, but sometimes what they're really looking for is going to be the proof behind the answer. So if they ever tell you to prove something, that's what they're looking for. And we'll do more proofs. You'll never have to do one by yourself until I feel like you're ready. Right now, you're not ready, but it's okay because you could follow my understanding here, which is what I was after. Okay, let's talk some more about definitions. I'm not going to make you sit through that. Hold that thought. Okay, so I think I'm ready now for this part. It's a whole bunch of definitions, but I wanted to go over them and point out some things about them. So a line segment is a segment connecting two endpoints. Here we're talking about the line segment ST. If I wanted to write line segment ST, then I'd have to write my S and my T, but we learned a few minutes ago that that is talking about the distance between S and T, not the actual line segment. So if I wanted the line segment, I have to put the bar over it. Now, back in the day, I would be so picky as to want a little dot there and a little dot there so that you knew that it stopped. I'm not quite as picky now because I'm more interested in saving time, which means just a little bar is fine. It implies that there is no arrow and therefore it cannot be the line ST. Is talking about the line segment, which is just the distance or just the segment from here to there, nothing on either side of those. Now, there is another way of writing it. I don't have to write ST. I could turn it around and write TS. Same thing, talking about the exact same thing, the exact same line segment from ST. This is talking about the same thing. It doesn't matter which way you write it. They are the same thing. Think of it kind of like the reflexive property. Array, however, is different. Array is a segment that has an endpoint, like at S, and then continues forever in the other direction. So we could talk about ray ST. I'd have to put the arrow over the T to say that it starts at S because that's the endpoint, and it goes past T and keeps on going. That's why we put the little arrow over it, because it keeps on going. Now there is another way of writing this, the exact same ray, only I want to put the T first. Now when I do that, remember the arrow keeps on going past the T. That means that my arrow has to be on that side because the arrow has to be wherever the T is. So it's talking about the exact same ray, but usually people write it that way because we usually read from left to right. Now, I've talked about this particular ray, but there is another ray up here. We could talk about the one that starts at T and goes past S. If I wanted to talk about that one, that would be ray TS. These are not the same thing. Ray TS starts at T and goes all the way through S and keeps on going. Those two are the same. This is the same as ray ST. But they are not the same thing. They're talking about two totally different rays. So don't get confused by that. Both of these are talking about things, not distance. Now, when we get down here to talk about congruent segments, that does have to do with distance. So, and it's the things that are the same. So it gets a little bit confusing. Don't get confused. The symbol for congruent is that right there. It's the equal sign with a little squiggly on top. You can kind of see it. You can kind of not. Help out a little bit. There you go. The equal sign with a little squiggly on top. That's the symbol for congruent. So congruent segments have equal measures. That's our distance. And we mark these with tick marks. So if I wanted to say that segment AB is congruent to segment BC, that's saying that this thing and this thing are exactly the same. So they must have the same distance. That's what the definition of congruence is. But we're talking about the actual thing. We're not talking about the measure of the thing or the distance of the thing. We're just implying that they are the same. So a little bit of a gray area, just kind of roll with it, it'll work. When we're talking about the things, we use the congruent symbol. And these are what I mean by tick marks. Just put little teeny tiny marks on them to say, this one is like that one. Another thing might have two tick marks on it. Since it has two, it would be like the one that has two tick marks on it. So really, up here, instead of saying equal, because we weren't talking about distance, I should have used congruent and not congruent, because they're not the same. So down here, when we are talking about the things, this cannot be the same as that, because this only has one tick mark and that one has two. So that's going to be like with something else that has two tick marks. Down here, since it has one tick mark and it has one tick mark, that means that those two things are congruent. So we can look at the picture and tell that it's congruent, or we can look at what we wrote and tell that it's congruent. Okay, opposite rays are two rays who share the same endpoint but head off in opposite directions. In other words, it looks like it's a line. An example of opposite rays would be ray BA and ray BC. Are opposite rays. BA goes off in this direction, BC goes off in that direction, but it looks like it's a line, and that's okay. Midpoint is the point that splits the segment into two congruent segments, which means they have to be the same. So we have to be talking about the exact same segments, and they have to be the same distance, because that's what congruency is. It talks about equal measures of the same thing. So these were both segments, and they have equal measures. That's what made them congruent. Since they are congruent, that means that B is the midpoint of AC. And I'm talking about the segment AC, not the distance of AC. Since it's the midpoint and the midpoint splits it up into congruent segments, if I wanted to talk about distance, I could. I could say that AB equals BC, meaning the distance from A to B has to be equal to the distance from B to C, because that's what a midpoint is. Okay. I'm hoping to get the rest of it all on one page, so just be patient. Won't take but a sec. And for the last part, I hope. So, more theorems. Every point on an array is some distance from an endpoint, and every segment has one midpoint. As far as we're concerned, all theorems, corollaries, and postulates work the exact same way. There's nothing fancy about any of them. So it doesn't matter which one derived from where. What we care about is that it's an actual fact. So both of these are facts, and they're both kind of facts you're probably never going to use, but they build the things later on, so we need to write them down. Bisector of a segment is another definition. Any line, segment, ray, or plane that goes through a midpoint is called a bisector of that segment. So if I had a line that went through M, we would say that line bisected AB because it goes directly through the midpoint. If we had a plane that went through it, we'd say the plane bisects AB because it goes directly through the midpoint. Now, let's take that out so we can actually read it. Put my M back. Okay. And then we have the midpoint theorem, which we're probably always going to call by midpoint theorem, because when they give it a title, there's a purpose for the title. It's actually making your life simpler. So that when we refer to it later on, we can just say midpoint theorem instead of all the other words that go along with it. So the midpoint theorem says if M is the midpoint of AB, then AM must equal MB. I showed you that in the previous part. But here, if I have AB and M is my midpoint, that means that this section has to equal that section. Because of that, you have a few other things that it means. It means that two of these distances is equal to the largest distance, or two of this distance is equal to the larger distance, or half of the larger distance is equal to one of the smaller ones. All that is stuff you know. I know you know. It's intuitive. That's the best part about geometry. It's intuitive. You already know this stuff. But there are things that we have to be able to say to prove that they are what they are. So the midpoint theorem is what you would use to prove what you already know. Now, let's look at problem number 31 out of your book. They said that the points A, B, and C were collinear and that B was in between A and C. Whenever they give you a problem and there is not a picture drawn, that means you need to draw a picture. If there is a picture drawn, then you need to draw that picture in your notebook so that you can have it there to look at later on. Otherwise, you're going to be, where did I get this stuff from when you look back at it? And that's not going to be helpful. So go ahead and draw the picture. I'm telling you, it's the first step in any geometry problem. Draw the picture, always. If you have a proof, draw the picture. It helps. I promise you it helps. Okay, so this is the picture they gave us. Then they gave us this information up here. They said that AB equals 24. That's my distance between A and B is going to be 24. And that AB was the same as 2/3 of AC. And they want to know what's the distance from A to C. Well, my AC, we're going to call X right now because that's what we're looking for, the whole algebra thing. That means that I'm going to let AC equal X. And since we know that AB is equal to 2/3 of AC, I can substitute in place of AC and put X. So that means that AB is equal to 2/3 of X. And we know that AB is really 24, so I can substitute this AB and put 24 is equal to 2/3 of X. Then I could multiply everything by 3 to get rid of my denominator. 3 times 24 is 72. And then 3 times 2 is 6. Divided by 3 is 2x. Then divide everything by 2 to get x by itself. And x is equal to 36. Which means that AC is equal to 36. Now, you didn't have to show me all that. I had to show you all that. I would have been okay if you just would have come up with what the answer was, because I know you can do that in your head. I know you've got these skills. I know you know what you're doing. Don't get me wrong. I have all faith in you that you could have done this problem without me. But I had to show all this because later on, they're going to be asking you for reasons why all of this stuff is true. And if we don't have all this stuff written down, then we can never find the reasons for them. Kind of understand a little bit? Not fun, but that's the way it goes for right now. So, tomorrow you have a quiz. It's not a long quiz, got 10 problems on it. Your mom already knows what it is. If you'll take your book to her, she can highlight what the problems are, and you can go ahead and take a quiz whenever you want. But that's what you're doing on Friday is the quiz. Next week, we will do 1-4 and 1-5 on Monday and Tuesday, and then you'll do 1-6 and you'll review for your test. It's going to be on Monday. So you need to make sure, since you're reviewing for your test, it's going to be on Monday, that you do the review on Friday, because that's what your goal is for Friday. But then come Sunday or right before you take your test on Monday, you look back over it. You don't have to redo it, but you do need to look back over it. Look back over some information, do a little bit of studying for it before you go into that test. Don't try to go into it cold, serious test. Okay, I will see you sometime, but you will see me on Monday. Bye.